That's my
Got to keep it light, otherwise people start getting. Yes, they are orange.
having orange tree at home. Oh. It's very tiny though. It's very tiny. It's a 8-year-old.
Yeah. Oh wait. Question before we get started. Y'all hated the moon yesterday? Only Nova came. We had an open house. It's on the schedule. People asked for it specifically when they couldn't go to the Thursday one. I had like 6 people come who are the people who work for me, and I had 1 person from the class come. It's okay. I hate me too. So let's talk about this week. So we're going to finish talking about a little bit. I mean, so even though we talk about like 10.2, 10.3, 10.5, this is all just atmosphere stuff. And we're going to try and get through it as much as we can. That being said, I don't know if we'll be able to do this one. I'm going to put this one here today. That's what I brought. I printed both. So worst comes to worst, you'll get it like this day. I want to be able to do both of these before we get through the whole process. If you look up here in the top right-hand corner, you'll see that it does say ASTR 1000 midterm 22. So I started writing it. There's questions. I think they're good. I hope you think they're good. Do people have a preference for more or less questions? Less questions? Worth more? More questions, worth less. Oh, shit. Yeah, you still got to get 100, right? So it's just a question of how you get 100. Do people prefer shorter exams that are worth more or longer exams where every individual question is worth less? Yeah.
What would be short?
So short would be like 4 questions with 3 parts each.
And longer?
Long would be like 7 questions with 3 parts each. You like longer? Okay. So if you don't like it, come up to me at the end. Let me know. Because the nice thing is I can ask sort of the way that it's built right now. It's very straightforward. I'll ask you some question like explain to me such and such a concept, right? And I want it in your words, what you've understood from the class. Okay. And that's how you sort of gauge your understanding. It's the same way that all of these have worked, right? It'll say stuff like, student A says yada, yada, yada. Do you agree with them? Yes or no? Why? And if you just say yes, you get no credit. You say why, you get credit, right? Well, no. You're trying me today. Okay. So we're gonna do one of these today, hopefully, and we're gonna try and get through a lot of climate stuff. Of course, anything that I don't get through will not be on the exam. Questions, comments, concerns? Okay, let's get started. What's this? That's a hurricane. Which hurricane? No. What's that? Yes, this is Hurricane Ian. So again, unfortunately, when I teach this class, the whole world falls apart. Every time that I teach the atmosphere part, hurricanes are just pummeling the South of America. Not South America, South of America. And is this, you can see these state lines from space? No, they didn't like put white chalk like they do in football games. No, this is in fact, it's called a computer graphic. They put the computer graphic on the image. And you say, well, if they made the computer graphic on the image, and how do you know the whole image is fake? Okay. Anything interesting you see here? Yeah, is there anything that stands out to anyone else? The way the water is at the equator here? Yeah, there's like little like puffs and clouds everywhere. Did you have a question? Yeah. Yeah, so the swirl like goes this way, right? So it's like spinning this way and it swirls all the way up. That's kind of cool. Yeah, in fact, right over here, you know, that's where it ended up moving this way, smashing across Florida in this direction, and then smashing and leaving a lot of rain there. Anything else that's fun? You see another spinny news? There's one system that's spinning, right? Which direction is it spinning? Counterclockwise, right? So if I take my thumb and I put it in the eye, you can see, okay, it's rotating this way because I can see all of these here spinning around. Just like if I were to take a mop, spin it in my hands, that's what would happen. Yeah. That's a homework question. We'll explain it today. We'll explain it in like 5 minutes, but you'll see that that's actually in the homework. You're like, okay. Okay. So let's keep our brains nice and warm. So based on the figure, you've all done the reading. You all studied the lecture material afterwards. I know as soon as you get home, first thing you do, you open up the lectures when I post them, and you start rereading the material, of course. Yeah, good, everyone does. And so the question is, we talked about the different layers in the atmosphere. Where was the troposphere again? Is the first one. So it's the one that we exist in, unless you're having a really bad day, in which case you might be in the exobase. So here we're going to say, based on the figure, do you expect convection? What was convection again? Yeah, what's an example of by convection? Boiling water. I like miso soup, but let's do boiling water. Do you expect it to be more or less active at Mars than at Earth? So on the picture to the right, you see there's temperature versus altitude. We recognize our blue shape here. The tropopause, or sorry, the troposphere is in the lower part of this. It's called the tropopause. We won't talk about that, just the part where it comes one from the other. And we said, okay, we can get convection for Earth just down here in the little part. And the question is, do you expect it to be more or less active at Mars than at Earth? See your fist for the vote. Vote on 3, 2, 1. Okay, I see less active, and I see a couple actives, and 3 the sames. What do you think? Are you framing these? Also ask a question, clarification. Are you voting or are you asking?
I'm gonna answer.
You're gonna answer.
Yeah, I said less because if there was convection on Mars, you see incline in temperature, and then you see it again, or well, it would start at a high temperature and would move to a low temperature, and then back up.
Okay, do we need it to move back up again to get convection?
No.
No. So if we have boiling water, we have hot on the bottom, cold on the top. Do we have that at Mars? No. Where do you see the Mars thermal profile here? Where does it start at the bottom? Minus 56. Now, given that's cold, right? But what happens to it as you go up in altitude? Yeah. It actually gets colder. So notice that it's going backwards towards minus 200. So it starts off hot at the surface and gets colder. Okay. So is there convection on Mars? Yes. Okay, hot at the bottom, cold on top means you can get convection. Okay, where there's hot on the bottom, cold on top, because hot rises, cools, and then falls. Heats up, rises, cools, falls. Right, that's the convection. Okay. Okay, all right, now it makes more sense, right? Okay, so would you say it's more or less active at Mars? You still say it's less?
Even though it has convection, it's not the same. It's not a very drastic conservative.
Yes, okay, it's much more gradual, it's much more smooth. Okay, so that's what we're looking for too. So not only is there a difference in temperature, it's also steep, right? So that's like sharp. Oh, Venus. I know that's not on that's not the question I'm asking you about. What?
It's more active.
You think it's more active? Someone agree?
I think it's super.
Okay, so here's the question. How can you tell steepness here? Let's do a, need a stick. No one has a long sword. What? This is gonna work. It's kind of like a stick. Okay. All right, look at this part here. Okay. So that would be like how steep it is, right? Because if I were a skier, I'd fall down this. This is actually quite steep. Right? But it's not very large in temperature. So here I have a large temperature gradient over a small distance. This one's a large temperature gradient, but also over a really big distance, right? So here we have very active convection, is a large temperature over small distance. And this one here, it's actually kind of comparable, right? So notice if I just move it straight down, well, let me see if I can do this properly. I don't know if I did that properly. Right? That was the, can you see that coming back? The gradient is actually slightly steeper on Earth. Okay. We'll talk about Venus in more in detail. Venus has really weird weather for a totally different reason. Okay, everyone's brains are awake now, right? Okay. All right, so remember, this is what we want to, from the light and atmospheres part, we're going to connect these two. Going to try and put these together in the same way we did planetary processes and the things that we can see, like the size of the object, how far away it is, and the rotation rate. And then today, we're going to take the rotation rate, we're going to add that in. We're going to make this whole wonderful model in our brain of how planets work. Okay? So up here, we were talking about how X-rays break apart molecules, they break apart atoms even. Down here, they might like take your hydrogen off or ionize it. Down here in the visible, mostly doesn't mess with any sort of atoms, just passes through so we can see good. And then at the bottom, this is the microwave. It's heating up my burrito with making the water inside of there warm up, rotate quickly, and pass kinetic energy. Okay. And so if I understand how those increases in energy work in the atmosphere itself, I said that I could understand all of the thermal structure. Okay, good. So at the bottom, this is where visible light makes it all the way down, is absorbed, right? Talk about absorption. And then it emits because it's hot. So something that's emitting in the infrared because it's warm, then gets trapped down here, helps to heat the atmosphere, makes these nice convection patterns. Okay, that goes backwards. Now, normally, if there are no other type of light, what would happen to this temperature gradient? If it was just visible and infrared, no other types of light in the whole world. Yeah. What's that? Yeah, we'll just keep going. I mean, no reason. We'll just get colder and colder and colder until infinity. Okay. But in fact, what ends up happening is because it's catching these UV rays, it turns back up. What's doing the catching of the UV rays here on Earth? Ozone. Okay. There's a song, something about the hole in the ozone layer. Right? That's what this is. Ozone is literally catching ultraviolet photons and heating and putting heat into the middle of the atmosphere, 50 kilometers. You remove the ozone, what would happen? More UV light would come down to the surface, temperatures would go just backwards. If there was heating at the top, it would be a straight line that connects these two. Okay. So that explains what happens to UV photons and X-ray photons as they come in, they're smashing into everything and they're heating up. In fact, almost all atmospheres at the top are doing this, they're going off very, very hot. They're also not very dense, so they're not dangerous, right? You're standing at the top of the atmosphere for some reason, it's 1,000 degrees, but maybe 1 or 2 particles are hitting, so you're not that worried. Okay, you keep going, you get to something called the magnetosphere. We won't spend a lot of time on this, mostly just because we don't have enough time. And we're just going to show like what we like about it. Maybe when we get to Jovian plans, we can talk more about it. Here's the Earth. The magnetic field of the Earth is basically blocking strong solar energetic particles, stuff that's being emitted from the sun at very high velocity. And I wrote this up here. It's actually contentious. So scientists both see this as a benefit and a non-benefit. So for example, Mars does not have a strong global magnetic field. So it doesn't have one of these beautiful, like butterfly or apple looking magnetic fields, and particles just smash into the atmosphere, okay? But the Earth sees kind of the same number of particles, and while this picture might look like most of them are deflected, that's not always the case. Sometimes they're funneled directly along these holes, and those create aurora. And that can also be really energetic and make the top of the atmosphere very warm and make you lose the atmosphere as a whole. Thankfully, we don't live there. So if you lived almost exclusively at the North Pole, you might be at slightly higher risk over millions of years, but very few things live at the poles, right? And I'm not talking about like Anchorage, that's not poles. I'm talking about like the poles. Okay. All right. Let's go. Okay, so these are the things that they see. So sometimes if you get lucky, you go and see the aurora. They're beautiful. We won't spend a lot of time on them in the purposes of atmospheres. Okay, they have really cool colors. The colors are telling you what? What the atmosphere is made of. So we talked about spectroscopy and how we can use the light as an information carrier. That's what's happening here. So you're smashing into oxygen and nitrogen atoms, which give very distinct colors, greens and blues and reds. Okay. Just like, whoa, so cool. Okay, that's enough. All right. So different wavelengths of light interact with the atmosphere. You give it all of the basic things that we see. And we're going to talk really, really briefly about why the sky is blue, because that's one that like you may have never thought about before. And then we're going to talk about weather, how that's different from climate, and why we can use these to think about, say, Mars and Venus and the Earth, right? The objects that we have near to us that have substantial atmospheres. Okay, so why is the sky? Yeah. Okay. So we're almost there. It's definitely light from the sun. There's 4 processes that we think about. Is it reflect? Scattering. Okay. So remember, there's absorb, there's emit, There's transmit, and there's scatter. Okay, so we're going to use two of them to discuss why the sky is blue. So if I'm standing in Hawaii, beautiful vacation, it's noon. I look straight up, okay? The sun's over here, it's that big yellow thing in the sky. What happens as it enters the atmosphere is it bounces in to the pieces of the atmosphere. Blue light prefers to bounce off of those ones more than red light does. What ends up happening is it bounces out of my line of sight, but then maybe it bounces again, and it bounces back into my line of sight. And I see the sun mostly as white. Okay. But if I look off away to the side, I preferentially see blue. Because now this light that was scattered out, just like a prism, and then scattered back into my line of sight, looks like it's coming from all directions. Does that make sense? So it transmits red very easily. That gets down to the surface. Blue gets scattered a little bit, but mostly makes it blue. Okay. Now if I move over, sunset now in Florida, and I look to the right, the amount of atmosphere that the light had to pass through is actually a lot longer. Okay, think about it this way. This is 1 foot here. This is like 1, 2, 3, right? So it's substantially more atmosphere. The calculation is actually like 42, but the picture not very good, right? Does that make sense? So what happens to a single piece of light? See a red piece. Let's follow it through. Red piece mostly doesn't do anything. Makes it all the way to our eye. What happens to a blue piece? Oh, blue piece is going along, hits light, bounces, 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 and goes and joins this dude over in Baja California. Okay, so as we watch the sunset today, you'll see this exact phenomenon. Okay, the sun is actually going down, and the blue light is getting scattered before the red light. And so then it bounces off of stuff that's near us, for example, white clouds that are typically reflecting all of the light, now don't have any of the blue light to reflect you. They can only reflect you red light. And so they look pink and orange and red, right? Does that make sense, or did I lose half of you? Good. We like? Can I explain this to your friends now, or no? If you got an exam question on this, you good? Most lukewarm I've heard on this class. Okay. All right. What else do I want to say? Do I want to say anything else? We could talk. No, I'm not gonna do that. All right. Let's talk about weather. This is what we started with. Back to Florida. I'm just obsessed with Florida today. So this is another picture, right? From the spacecraft. Let me see. 3 hurricanes. Yeah, that's good because I put the names on. What else do we see? Like this one and this one? Okay, they're friends, yeah. They're like holding hands. Okay, cool. Anything else? What about their spin? It's the same way. Is that weird? Okay. Why do they spin at all? Yeah. Okay. You already did the reading. All right. All right. What else? Are we gonna ask a question like we talked about Venus? Venus is big, big atmosphere. What do you think about the winds there? Strong at the surface? Think they would be here on Earth? Why not? can't all do the reading. They're not really good questions. All right. So the question that we want to ask is, how does the atmosphere respond to the planet's rotation? Okay. And in fact, we can see this with something that's called the Coriolis effect. You heard about this? Okay. Thankfully, I have one thing to show you today. Video. Everyone likes videos. And I'm going to talk over it because I don't like his voice. Right. So essentially what we're going to do, I'm going to show you a video of 4 people on a merry-go-round. Okay. They're going to spin on the merry-go-round and they're going to throw a ball straight. So while it's not moving, you would assume 4 people on a merry-go-round. If I throw it to one of you, you would just pitch it. Okay. What happens when the merry-go-round begins to spin? Is the same person pitching? No. Everyone knows this because we've all been on merry-go-rounds. They're like falling over. We don't know what the hell's happening, right? So in a rotating reference frame, when everything around us is moving, straight motions don't look straight anymore. Okay, we'll see this in 2 seconds. Please work. Okay. Let's go back. Okay. Wait, let's do it. Okay, good. Okay, so he's going to throw the ball straight. And the question is, where does the ball end up? Is it caught by the person who's throwing? Is it caught by the opposite thrower? Hey, I have to flip. Oh God, where'd it go? Don't give the solution away. Hold on. Let me just go back 1 second. God, okay, let's go back. Okay. Okay, so is the ball going to be caught by the person who threw the ball? Is it going to be caught by the person who they're intending to throw the ball to? Is the ball going to be caught by the person on the left or by the person on the right? You already saw it. You ever done this before? With personal experience? They throw a sort of hand your friend on the ground. Empty. God, like, what if they wanted you drink some soda? What if you hit someone else on accident? Okay, so what do we want to vote here? Ready to vote? On 3, 2, 1. Okay, so no one liked ball caught by throw. No one liked ball caught by all. They're just left and right. Anyone want to argue for either of these? Just watch a video and say, hurry it up. Give me the answer. Anyone want to defend left or right? Yeah.
I put left because the first in a circle, but it's going at a certain speed. So if you throw it across, this is going to pass it. You can't have to yourself because most likely you'll need to help it. So most likely you'll need to listen to it off because they're doing at a certain speed for everyone.
Right. So this motion was really important, right? This motion is really important because if we hadn't said which direction they were moving, it could be either, right? So the fact that they said we're going to rotate clockwise or counterclockwise as seen from above means that if I throw the ball straight, where am I going to go to, if I take the ball, and this is like 1 second after me, then where do I go? Right, I'm moving like that. So what does it look like to me if this happens? The ball moves to the left. Does that make sense? Let's see if that's wrong. That'd be a really bad explanation. Okay, let's see. Okay. So they're going to throw the ball. To the right. Okay, there's the ball. Okay, so what's going on here? Should we look at it again? The ball has an yeah. Go ahead. Yeah. Okay. So the ball still had the inertia, right? When I'm moving like this, it's not really moving. So the problem is this thing is still in motion. No other force is acting. We talked a little bit earlier about Newton's laws of motions, object in motion, remain in motion, and I'm the one that's curving. So if we thought about this as an air parcel, a piece of air that's going straight, if the world moves underneath it, it will appear to curve in the opposite way that we would in theta. Okay, so let's look at that picture then. Okay. So the Coriolis effect essentially does this. Okay, in the northern hemisphere, air curves to the right. In the southern hemisphere, air curves to the left. And near the equator, it moves very little at all. You may have heard that as you go visit your friend in Australia, that the toilets spin backwards there. Is that true? No, it's not. They simply just go whatever direction the toilet manufacturer created. Because otherwise that would mean that people at the equator would not have toilets that went down in either direction. The water is straight. And that doesn't clean the bowl. The reason that it spins at all is because it's trying to scrub the bowl as it goes down. Same thing's true of your drain. Okay, your drain sometimes flows just straight in, but usually it rotates. Doesn't have anything to do with Coriolis. In fact, to see the Coriolis force requires massive distances. So this is why on a day-to-day basis, if I throw you something, I don't have to correct for the curvature of the earth or rotation rate of the earth. But if I wanted to shoot something, say, a mile away, I couldn't aim at the thing that I wanted to shoot. Because depending on my latitude, I would have to correct for the fact that by the time the bullet got there, that person would be gone, or the thing would be gone. Does that make sense? Okay. So this is this rotation rate is going to intensify the scrolling pattern. So for example, low rotation rates, not moving very fast, you're not going to see that happen at all. Right? You're standing still, it's a great example. No Coriolis effect, right? That makes sense. I'm going to state this without a lot of like justification. I know sometimes it's like, okay, let's walk through the whole physics of it. This is complicated, it's fluid dynamics. If you want to, you can take a class on it another semester, do fluid dynamics. No. Okay. But if you anyone else, okay. Let's think about these processes. Okay, planetary temperatures. In the absence of greenhouse gases, does the planet's average surface temperature, not the interior, the exterior, does it depend on size? Yes. What? Okay, but in the absence of gases. Yeah. Right, so that would be for the interior. Right? People are getting where I'm going with this. The answer is no. So an object that is large versus an object that's cold by a fire will both be the same temperature on their exteriors. Right? Now, what about distance from the sun? The fire in that example. Okay, that one makes sense. You put it closer, you get warm. You put it farther away, you get cold. Right? Okay. What about rotation rate? There's another word we want to check here. This average. Okay. So when we think about the rotation rate, it's going to average out. It's spinning quickly, then on one side it'll be hot, but only for a little while. The other side will be cold, but only for a little while. Versus if it's moving very slowly, be hot on one side and very cold on the other, and the average between them will stay the same. Does that make sense? But this really, really matters for day-night differences. So if you're spinning very quickly, it's almost the same temperature everywhere. If you're spinning very, very slowly, there can be huge differences in the temperature. There is a body that we know of. We actually see it quite often. That spins very slow. Yeah, we don't see that one. This one we see all the time. You don't even realize how often we see it. The sun, the moon. The sun you do see all the time. That's a very good guess, not what I meant. The sun actually moves very rapidly. We'll talk about that in the 10-10 line. This one here, the rotation rate of the moon is slow. Yeah, good. It's about 28 days. So it orbits once for every time that it makes a full rotation. That's why we always see the same things. Okay. So if you're living on the moon, you have a nice estate there. For 14 days, it's really cold. And then for 14 days, you're basically staring at the sun. It's really hot. Does that make sense? So those day-night differences are massive, as opposed to us, which, you know, sort of average out a little bit better. Okay. What's this word? Just put it on the screen. Right? What's a green? Anyone here familiar with green? Yeah, what's a green? Yeah, it makes it hotter. So what's special about a greenhouse? Is it green? No, not actually green. What is it actually? It's glass. You have a sort of greenhouse that you'll probably go back to in about an hour. Yeah. Traps heat inside. What greenhouse are you going to go back to in about an hour? Everyone listens to their watch. Your car. That's exactly correct. You get back to your car and like, it's so hot in here. Why? Why is it hotter in your car than standing next to it? Because of the glass. Because of the glass. What? That doesn't make any sense, Mateo. Okay, so this is the greenhouse effect. Okay. So this is light interacting with gases. And in particular, when we talk about the greenhouse effect, we're going to talk about different types of light interacting with different types of gases. In our example, we talked about solid materials that can transmit light, but for the purposes of what we're about to do, this will be the same. Okay? Okay. There's one person has to say, okay, and then I'm move on. Okay. So let me ask you a question. What temperatures do you think there would be without any greenhouse effect? This is the same picture we had from before, just change some shit. You think they'd be just like straight flat down? Okay. Which of these would change the most? You think Earth would change them? Okay. This is where they should be. Okay. Earth should be about 16 degrees. Venus should be about 40. And Mars should be about 56. Venus is way over here because it has a massive greenhouse effect. It has about 90 times the atmosphere that we do. And it's all CO2. You can't even see the surface. You can't see the surface. Visible light. That means visible light not get from the surface back out. And we're going to see how that affects this in the form of infrared light. Okay, so we talked about this part. Come on. Okay, talk about this part. Right, light can interact with the right size molecule. And for the most part, go ahead and ignore the ultraviolet and X-ray part of this. We're going to talk about the interaction between visible and infrared lights. Because visible light likes to travel through stuff really easily. Travels through air really easily. Travels through glass really easily. That's why we use it. But glass is opaque. Infrared light can't go through. It gets trapped. Okay. So this is what it looks like. Light comes down, heats up the surface. Visible light doesn't care that there's an atmosphere. Just moves right back down. Now some of that bounces. What's that called? Four processes. Sorry, there's four processes: absorption, emission, bouncing is bouncing off of atoms and molecules and scattering. But bouncing off coherently is called reflection. You can see me because of reflection. Light is reflecting off my face and into your eye. Okay. And that's what's happening here in this yellow line. You get light coherently coming out. But some of it gets absorbed. That's the red stuff here. And then emitted as infrared because it's hot, right? Now that infrared light loves molecules. So it's just like, you know, the social butterfly, bumping into all the molecules it can, try to get as many friends before it leaves. Yeah. Like in your car.
Yeah, not like in general, like what we have super hot.
Yeah, so glass getting hot, it's trying to get rid of infrared radiation, but it can only do it from a certain level. So it has to conduct through the piece of glass and out to the edge. Okay, so we have social butterfly trying to jump, bounces into all of these, and it's transferring heat. It's heating up the bottom of the atmosphere. Okay. Now, this is a idealized picture. So they're just little spheres. Okay, that's not really what an atmosphere looks like. Got a bunch of different stuff in it. And some of that stuff really likes infrared light, and some of it doesn't care. Right? O2 doesn't really care. But stuff like water, it really likes to warm up water. We already talked about the burrito, right? In fact, water is one of the best greenhouse gases. You know, warm up the earth, a bunch of liquid water vapor in the air. It'll get nice and hot. Okay. Question? You're all experts in greenhouse gases now, right? Just think to your head, straightforward. This is why my car is hot, except for instead of glass, it's gas. Okay. Cool. So what are they? As I mentioned, water is the primary one. CO2, secondary. And then CH4, anyone know what that is? Methane, where did that come from? Close. What? Cows what? Cows farts. So, does it matter? Yes, it does matter because the poop is not trapped. The methane is not trapped in the poop, it's trapped in the farts. Yeah. The gas. So it's gas. Interestingly enough, methane, a lot of people want to potentially use it as a biomarker. Be like, if you see methane, for example, in a different atmosphere, and say, well, something pooped it or farted it, right? What percentage of the methane on Earth do you think comes from cows farting? Like biotic things, as opposed to naturally. A lot. How much? It's like 80%. So almost 80% of all the methane on Earth comes from farts. Okay. Okay. Now, if we look at the content Okay, so here's mostly nitrogen is what I'm breathing. 78% nitrogen, 21% oxygen. Okay, so that's great. Wait, add those numbers for one. What's that? 99. So thankfully, it's not like 20% far, right? That would be uncomfortable. These are trace gases, a small fraction. In fact, these are the fractions. Here, it's about 0.25 H2O. And that's that relative difference that you'll feel on a dry day versus a hot day. Small changes in that. Here's CO2, thankfully also very small. If that were really big, what would happen to us? Just like in this room, if I just switch this number with that number. What happens if you only breathe CO2? You pass out and you die. You die. You asphyxiate. We use oxygen. We turn it into carbon dioxide. If you took this much CO2 and turn it into all water, you would have a really bad day. Okay? Last one that goes away. And here's farts, much smaller. Okay? Now this is the total content. So of course, if you're out on a nice spring valley hike, these CO2 contents are really low. If you're in a room full of people, that might be higher. If you're next to a factory farm with cows, that might be massively high, right? Okay, what about Venus? You remember what the primary constituent of Venus's atmosphere is? I heard CO2. That's correct. So it's 96% CO2. Second constituent. It's actually, yeah, I think it was 4%. Yeah, 4%. I don't have it in here. Damn it. Yeah, so there's another slide of that. Anyway, Mars, 95%. Not as much, but some. So if we think about it in this context, what would the Earth look like? The temperature profile. How would that be affected if there were less greenhouse gases? The line in the troposphere would be more steep and start at the bottom at cooler temperatures here, going up to there. The line in the troposphere would go to higher temperatures at low altitudes. This way. The bump in the stratosphere would be warmer, like this. The bump in the stratosphere would be cooler, like this. Or the temperature in the thermosphere would be warmer, like over here. Let me know when you're ready. It's like a perfect example of an exam question, right? You might have all these different thoughts. Seems hard, but I could probably do it. You can get this. These are found online in Canvas. You have them, right? I don't have to take a picture. Okay, all right. Yeah, okay. So let's vote with our fists. Let's vote on 3, 2, 1. Okay, I got some of you, but you're mostly between two choices here. Got a lot of people on 4, a lot of people on 1. Some people on 2. All right. Let's go to a lecture tutorial on this topic. We don't all fall asleep. Let me take this. Sorry about the copying. It's I don't know how to turn the words. Wait, so you can share when you work together, right? Yeah, I don't have extra. If everyone has their own, then I don't have any for the people who decided that they hate me today. So okay, try and grab a partner if you don't have one. There we go. Thanks, Ella. You guys are gonna work together? We work on this. Wait, you have someone to work with? Why do you ask about it? No, make a new friend. Make a new friend. No, in the back. I don't know all you. Yeah, phrase it before. See your pocket. If you get to the next page, repeat it. Don't do it twice. You think I do my own printing? I don't. Oh yeah. Okay, we're good. We're good. Just pay attention to the numbers. If you see the same question, it might be the same question. Yeah, so the 7% of the total. So which of these give them? Which of these? And then you add. You don't have to do the whole thing right now. In fact, you won't. I try my best. Yeah, I don't understand this part.
Yeah, it's exactly opposite.
Like, this is very strange. What's that?
Like, it's like their knowledge, so it's kind of like giving nerds. So you can't ask people for like information about it, but like it's giving your thought.
Yeah.
Process.
But so they're supposed to like walk you through that. Like,
I feel like they're not walking you through anything in their argument. I'm kidding.
be nice to them. I don't know.
We'll come back to it later. And then have both private. If they come. It's actually kind of fair. Maybe
Good number.
That is, but it's not a that right. Visible light. Yeah. It's over. Sorry. You're supposed to tell her that.
I know it's good you're in, so. Still limited to all.
It's because it's right. Yeah, right. Get the board. That's too, there's like. Yeah. If it's like this.
About like
How many questions on that?
An hour?
No. I had an hour. Again. It's the same as that. Now it's the same as that. Yeah, this one has equal somebody. Which one has and then with list. Okay.
Yeah.
Not remember. It is not this one.
Okay, folks, so let's put this down for a second. We're going to keep talking a little bit about atmospheres. We can finish it either individually or at the beginning of next class. And I'll talk just a little bit more about the exam. And then we'll go have a nice weekend. Okay. Not Dennis? This baseball playoffs are here. What? All right, right away. That's 2 strikes. Okay. So first question is, we're actually gonna leave this one until we've done the entire one. First question is, when we're thinking about like these average surface temperatures, rotation rate's really not that important, but it turns out that reflectivity is, right? So we can think about this in the context of something called albedo. So how reflective is something versus how much does it absorb? So compare the reflectivity. Oh, this is not a good example anymore. All right. Compare the reflectivity of these objects, which will get hotter quicker. The phone, because it's black and it's absorbing all the light that we can see, right? Whereas this is reflecting most of the light. Now, of course, it's absorbing some of it. That's why it has the temperature at all. And of course, this one doesn't absorb all of the light. Pretty good. It still reflects some that I can see. Okay. We call that albedo, and that's very important about surface temperatures, right? And this is just a measure about how much light reflects versus absorbs. So we usually say it's between 0 and 1. 0 would be absorbing all light, 1 would be reflecting all light. There really are no materials that reflect all light. They interact with similar. And unless you're thinking of like mantle black, you basically don't have anything with 0. Okay. Okay. You guys excited for the next question? No. Okay, good. All right. What would happen to Earth's temperature if it were completely covered in fluffy white nitrogen clouds, but still have the same amount of greenhouse gases as it does in math? Would A, the temperature go up? B, the temperature go down? Or C, dumb question, nothing would happen? Your fist. Ready to vote on 3, 2, 1. Okay, I see some votes for 2, some votes for 1, some no votes. Okay. And no votes for 3. So no one thought it was a stupid question. Does anyone want to defend their answer really briefly? Something more reflective, what happens to the visible light? Bounces off. It doesn't get absorbed and then become infrared light that would get trapped in the atmosphere, heating the atmosphere. So in fact, yes, the temperature would go down. As the reflectivity of the planet goes up, the visible light simply bounces off and doesn't cause us any more troubles. Okay, so let's think about that in this context, right? This is that picture we kind of showed before. You have visible light in on the left. It transmits through the atmosphere. It's absorbed a little bit, a tiny bit on the way in, but most it's absorbed at the surface. Some of it's scattered. Examples of scattering include why the sun is about to set and look beautiful, right? Versus reflection from clouds. So clouds tend to sit on top of this fluid that we live in, that we don't even see exists. They're good at bouncing light off. That's why we see them. We don't see the air. Bad at bouncing visible light. Right? Clouds, good at bouncing visible light. Okay. On the right-hand side, you see IR thermal. This is the stuff that we're getting rid of. So the surface starts to emit. It's hot. Hot surfaces emit in the infrared. And as it tries to get out, social butterfly bounces into all of this atmosphere, heats it up. Some of it just gets directly absorbed, fully absorbed in the atmosphere. Never makes it all the way out. And of course, some of it makes it all the way out. Okay. This is why we have this beautiful diagram. Here is the energy coming in. This is the thermal emission from the sun. Yeah, go ahead. Yes, but maybe not for the purposes of what we're talking about today. Let's not get bogged down. They would be nitrogen, they'd be fluffy, just so that they're not like another greenhouse gas. Right? Because if I added like a ton of water vapor clouds, then the temperatures go way up. Right? Okay. Good point. Good catch. Okay. So here on the left-hand side, we have visible sunlight. This is the reflectivity from the sun. So we get that color of the object in the first place, right? So most of this is absorbed here. And then it's hot, which is this stuff out here. This is the energy that it's getting rid of. And these little ups and downs, they mostly don't matter overall to the energy budget. They're small fractions of total energy, right? And what matters the most is you have visible sunlight in, heating up the surface, and then it becomes IR, and it escapes. Okay. Okay, so as we discussed at the beginning, we've talked a little bit about weather and climate. We talked about how the atmosphere gains energy from light. We talked about Earth's rotation, giving us these different pieces. We're trying to connect all of these things: rotation rate, distance from the sun, and size to the fundamental geologic processes that we see, including things like erosion. And you can't have erosion, you don't have an atmosphere. You can't have an atmosphere, you don't have a large enough size, you have volcanisms, right? So we're trying to piece all of these things together. We're going to go through that process probably at the beginning of the next class. So how do we gain and lose atmospheric gases? And whether or not this type of theory that we construct will describe why, for example, Venus would not be a nice place to vacation to. And actually Mars would be a shitty place to vacation to as well. Okay, despite what Elon Musk wants to sell you. So we're going to do that at the beginning of Tuesday. As mentioned at the beginning of this class, there will be an exam. Okay, everyone knows that. It'll be a week that you get to take home. Okay, you get to work on it. And based on the votes of people in the room, they wanted more questions that are individually worth less, as opposed to, wait, what's the other way? Less questions that are individually worth more. Does that seem fair? If you have a major problem with that, come talk to me now. Otherwise, your voice won't be heard. Okay, questions before we break early. Okay, have a great weekend. Yeah. Yeah. So what'll happen is I'll give it to you at the beginning of Tuesday's class. Maybe I should give it not during. I'll give it at the end of Tuesday's class. Yeah, because no one will pay attention to me, but we play their math homework. Okay, so I'll give it to you at the end of Tuesday's class, and you'll have exactly a week to give it back.
The following, at the end of class.
Yeah, no beginning.
Beginning or end?
Beginning.
Oh.
It's like what, an hour and 15 minutes? You're not gonna be doing it in class. Please don't do it in class. I have a couple answers.